Welcome to this module on power system models. Power system models are really now at the heart of transmission monitoring systems, reliability coordinator systems, and balancing authority systems. Years ago, basically, as a system operator, you would be monitoring the real-time data coming in from your SCADA system. You'd be looking at real status points, real analog points, real measurements. But remember, when we talked about situation awareness, there's really three main parts. There's the what is happening, actually measuring the right quantities. There's the so what, what's the significance of that? And then there's the now what, what's going to happen in the future? And for sure, the now what power system models are really essential. The power system is so large and complex, the human cannot anticipate and predict what will happen for different contingencies. You have to have power system models to do that. So the point of this presentation is to give you an understanding of how are these models built. How do these computer programs work? Because the results of those computer programs are becoming more and more essential for you to make good decisions as an operator. And you've heard the saying, garbage in, garbage out, or bad data in, bad data out. So as a system operator, you have to build your confidence in those models. And normally you go through a calibration and tuning up period. When that model is first put online, there will be errors in it. Impedances will be wrong, connectivity can be wrong. You as a system operator may be involved in actually testing out and checking that model. And it's really good to see the transition, that you go through a process where as a system operator you say, well, that's not right. And the support engineer gets in there and they fix it. And then you say, well, that's good. But then you get to the point where your initial reaction is, well, that program's not right. But then when you dig a little deeper, you actually say, hey, the program is right. It's anticipating some condition you hadn't thought of, and you start building more and more confidence. And so it's very important to go through that model tuning and calibration and get that model right to the point where you have the confidence in it. Now, there can be cases where the models literally don't solve. It's called a non-converged power flow solution. And we've had situations where it may be due to an error, but you cannot dismiss a non-converged situation too lightly. There was a case in the Northeast where the contingency analysis wasn't converging, and it went on for the whole shift, and towards the end of the shift, that contingency actually occurred, and a whole bunch of the system ended up blacking out, because the fact that there was not a solution from the program meant that there was not a viable power system state. So you as an operator have to be able to make that call under even difficult conditions. So that's why there's a really good motivation for you to have a good understanding of what's happening behind the scenes on those programs and understand what is making those models work. The presentation will have two major parts. We'll talk about planning models and operating models and how they have both evolved and why they're different. In the ideal world, there would just be one set of models that handled planning and operating. But for historical reasons, we've seen two separate paths in terms of the technology, and we'll cover why that happened. And then finally, we'll cover the Common Information Model, which started out as an EPRI, Electric Power Research Initiative, and then it has been adopted by the IEC, the International Electric Technical Commission, as a standard for a preferred way for modeling systems which is not dependent upon any proprietary vendor format. So let's look at planning models. The objectives on this segment are for you to be able to describe the applications of those models, describe the overall structure. We'll use a technique called the Unified Modeling Language to explain the structure, and then describe how the objects in those models are related to each other. Then we'll talk about the attributes, things like resistance, reactance, and all the different parameters that need to be correct so that that program gives good results. And then we'll talk about the pros and cons, or advantages and disadvantages of planning models. So basically, the applications for planning models can be long-term transmission planning. This can be in a time frame from 2 to 20 years, And as planning engineers, you're basically determining the routes and the capacity of lines, where those lines will be located, what's the rating of the transformers you need to put in place, and do you need megawatt sources to take care of the line charging during light load, as well as the load and the reactive demand during heavy load. In the nearer term, you can have 1 to 2 year planning, and basically you're assessing the capability to serve the forecasted winter and summer peaks, and you're looking at, is there a requirement to install reactors and capacitors? You're determining transfer limits, and of course you're always looking at the ability to withstand contingencies, and you're looking at how the flows on your system could vary as a result of power purchase agreements. This is an interesting map here showing all the transmission lines in the continental United States. And basically the purple is a 765 kV, and a dashed purple line is a plan for the future. And so what you'll find in general, if you look at this map is actually, the Penwell map is an excellent map to get oriented towards both the generation and the transmission in the US. All the different generating plants are shown as circles, the yellow being nuclear units, the red being coal-fired units. So we see a lot of coal-fired units along the Ohio River here. But basically, American Electric Power has a vision that they will build 765 kV lines to form a superhighway, the analogous to a superhighway structure throughout the US. We don't have that right now. The transmission lines literally grew up from individual utilities agreeing to take care of their own load with their own generation, and then putting in a certain amount of interchange with their neighbors. And so in terms of the ultimate, most ambitious scope of planning models, it's really to model this entire interconnected super transmission highway system that would connect large parts of the US. Now, we're not seeing a lot of new transmission lines going in the eastern part of the interconnection because it's clearly much more congested. What you're seeing in the east is transmission voltage upgrades. They'll take maybe a 138 kV line and upgrade it on the same right-of-way to 230. But clearly, in the western and the Midwest, there's a lot more open spaces, and you're seeing some very ambitious plans to put in very high voltage transmission lines to connect the system much more closely together. And clearly, with a lot of wind generation going in the Midwest, we're seeing a need to bring that generation to the load centers, which tend to be closer to the seaboards. So that's one example of a transmission planning power flow. You're literally modeling 10, 20 years out in the future. You're putting in these, you're conjecturing what will the flows be if I put this transmission line from this point to this point. Another use for the planning models is what's called operations planning. And in this case, you're looking from 1 week to 1 season ahead. You're providing studies. Should you allow or disallow a request for a schedule outage? Typically, a lot of the outages occur during the spring and the fall when you're not looking at the summer and winter peaks. But you can actually have a case where you have so much equipment out for maintenance, and also your generating units as well as your transmission lines, then you really have to run those studies, not only to determine that when that outage is approved, will the system be in within all limits, but can you handle the next contingency? And we've covered that previously. We're always running the system to deal with the N-1 and even certain more probable double contingencies. So you're looking at building preventative action plans. If that contingency occurs, what do you have to do ahead of time to make sure it doesn't cause overloads? You're also developing remedial action plans. If that contingency occurs, what steps can you take after it occurs to mitigate any overloads it may cause? In this time, you may be updating transfer limits with your available transmission capacity. We talked about the need to reserve available transmission capacity to take care of utilities buying and selling and moving power between each other. You can use these to train your operators. Typically, these planning programs are specialized enough that you have an operations engineer. The user interface for these programs is not so intuitive that an operator will actually be using them on shift. So we may have a dedicated operations planning engineer that is taking care of all these types of studies. And we'll get into the reasons about why that is needed later. And so after that operations planning engineer, after he or she has run all the studies, they have to get the operators together to brief them about, well, these are all the types of things you have to be aware of on your system. Another aspect of that is the operations planning engineer is typically an 8 to 5 job, 5 days a week. So if you're on shift and something unexpected happens outside of those working hours, you've either got to make it up for yourself, which is not good, or you may have to even call in the operations planning engineer to run those studies for you. Now, in the real-time operations, there clearly is a preference to have operating models running both the real-time and the operations planning. But not all transmission operators have those programs running. That's a very sophisticated set of software. You need to have specialists to keep them up and running. So there are cases where these planning models are actually used to run the real-time studies of 1 hour ahead and determine new operating limits in the event that a contingency occurs, update your preventative plans, develop your remedial plans. Remedial plans should really be developed in advance so that you know that if this occurs, then this is what you can do to counteract it. And then update your transfer limits and assess an approval for, say, an emergency outage where the person requesting the outage, it may be a case where there's actually equipment or lives are in danger, and clearly your goal is to get that approval done as soon as possible. So we'll go through the structure of planning models, and through that you'll get an idea of where their strengths are and also where their limitations are for real-time operations. But really, one of the basic distinctions for planning models is that, and operating models, is that operating models are automatically updated to reflect the real-time conditions. If a breaker opens, that model is updated automatically. A planning model is not automatically updated. An operator literally has to look at the real-time conditions and do a lot of data entry to set up the generation, the load, the system configuration to reflect the real-time conditions. Okay? So that is the primary difference. The other difference is that planning models are typically single user and are not event driven. The operator literally has to make a change, and then he or she sees the results back, and it's just their own private copy on their own PC. Operating models, they're event-driven. When something changes, that model runs automatically within a certain period of time, and then those results are available through the network for everybody to see. So there's some couple of major differences there. But let's look at the structure of planning models. Another main simplification is that planning models are bus-oriented. And what we mean by that, we can see it here with an example of the Crawford station taken out of the PALCO system. In the real world, we actually have a 230 kV breaker and a half configuration for the lines, and then a double breaker for the load. And remember, we said a breaker and a half is because we really have 3 breakers shared between two lines here. This is something that the system operator can relate to. He's been in the substation. He can actually recognize a bus section, which is 3 conductors, solid conductors, typically copper, which are actually 1 for each phase, A, B, and C. And then, of course, we've got the circuit breakers, which are huge air blast or SF6 or even oil tanks. So an operator can look at this diagram and be very clear. Well, that's breaker 5. I know that. I can see that in the substation. Even though this is a single phase, the operator says that circuit breaker will actually be 3 separate units, but they can relate to the fact that we've taken the 3 phases and converted it down to what we call a single line diagram. We have one line representing each of those 3 phases. But what we do in the planning model is we literally condense all of that. We ignore all the actual breakers and all the circuits, and we say, let's define a bus. And that bus is really an abstract view of the world. A bus is really all the things that are electrically connected. So in the normal configuration, all of these breakers would be closed, and a planning engineer's view is that I really have one electrical bus because everything is at the same voltage. A bus in a planning engineer's view is everything is at the same voltage. If for some reason the bus was to be split, let's say we opened all the middle breakers, then the planning engineer's view is, well, I now have 2 electrical buses, one here and one here, because they're now operating at the same voltage. This level of abstraction is really confusing to system operators in general that have come up through the substations. And so we see this dichotomy, that engineers are very comfortable with planning models and this abstraction, and operators just really have a difficulty running those programs. And so that's why we've had these 2 models. The planning simplification came about because of the fact that we can make some very gross simplifications in the computer programs and the modeling. And that was for historical reasons, when these programs were literally developed in the early 50s. And we had very limited computers, no databases, and so this became a really nice way to simplify the world. So to get into the underlying structure of these models, I'm going to use a technique called the Unified Modeling Language. This is a very popular language that is used in the system engineering and computer design world. And the idea is that through an object-oriented modeling language, we can specify and visualize and document the way software will work. So it's a way to describe software with diagrams. Why do we want to do this? Well, there's a statistic. More than 70% of the problems in software occur with a misunderstanding between what the customer wants and what the programmer develops. And it's not until years of work and all that effort has gone into it, the operator looks at it and says, whoops, that's not what I wanted. So these models, which are mainly graphical, reduce the complexity and facilitate the understanding. And we have the saying, a picture is worth 1,000 words. So UML is a concise way of showing how you model systems with diagrams that are really intense in terms of their meaning. It's a language which both the users and the programmers should be able to understand. So here, for example, is a UML diagram for a power system planning model. What we see here are a number of different entities. An object, which is the rounded rectangles, is a thing which is important to model the system, and it's something that the customer needs to relate to. And so in this case, we see that we have a bus, and we have branches, which are transmission lines, transformers, synchronous machines, shunts, which are shunt reactors or shunt capacitors. We can have DC lines, and we have the concept of the equipment belongs to a certain area, and those areas can be divided into zones, and we can have ownership. So if you're a user and you look at this diagram, and if there was something that was missing, you would know, well, the programmer has overlooked something. And so let's see, what's missing? Well, for example, and this is not complete, we don't have a load here. Okay, and that's just an oversight on my part. But again, as a user, you should be able to look at the things that you would expect to have in your system. We don't have a substation, all right? In the planning world, they didn't worry about substations, all right? Substations are really important to system operators. So that's an issue. So those are the objects. Now those objects have relationships to each other, and we show those by the arrows. So we see, for an example, that a transformer connects to a bus. And a transformer can also regulate the voltage at the bus, all right? That makes sense. A machine also connects to a bus, and it regulates the voltage. So that shows you how things are relating to each other. There's another aspect, is we can show what's called, in computer terms, the cardinality. And that is how many transformers, well, how many buses can a transformer regulate? How many buses can a transformer connect to? In this case, we see that it connects to either 2 or 3 buses. And that makes sense because we can have either a 2-winding or a 3-winding transformer. In this case, each of the windings of a 3-winding transformer could regulate 1, 2, or 3 buses. You literally could have taps that could model the primary, the secondary, and the tertiary bus. The other aspect is the star. That means that a bus can have multiple transformers connected to it. And that makes sense. A bus can have multiple machines. And so you just see through these numbers here and these symbols the amount of meaning which you can get out of that simple diagram. Now, the one thing we notice about this is that this abstract concept called the bus is at the heart of everything. Everything is connected to a bus. Everything is regulating a bus. And that one thing greatly simplified the development of the early planning power flows. Basically, it meant that we could number all the buses in our system, and not only did we have a way of identifying those buses, we could use those buses as indices inside our computer software, and everything became greatly simplified as a result of the fact that everything was attached to a bus. And literally, for decades, you could write really good planning software, and you did not need any sort of database manager. That's because of this simplification. In database terms, we would say there was only one primary key. Everything was related to the bus as a primary key, and because the database problem was trivialized, you really didn't have to have a database manager. So back in those days, this whole concept of relating everything to a bus for planning models became really fundamental. But again, this was an abstraction that the engineers are comfortable with, but the operators never really liked that idea. The planning engineers would allocate a certain region of the country. So literally, they'd decide to say, we can allow 100,000 buses for the eastern interconnection, and everything in the southern area is going to be buses 10,000 to 20,000. Everything in the Midwest is going to be 20,000 to 50,000. And they would deal with bus numbers. And to operators, those bus numbers made no sense at all. So so you can get an idea of how building something with an abstraction for the sake of making software simplistic did not carry over into operations. It was okay when you were running studies. In the planning environment, you have lots of time. You're not making mission-critical decisions. So this abstraction has been tolerated for a long time. The other aspect is that in the 50s, 60s, 70s, we didn't have nice graphical user interfaces. So literally, engineers were preparing models, data for these models using text files. And here's an example of what's called the raw file, which is the basic big text file for all the data going into a PSSE planning power flow. And it breaks up into buses. So basically, it's just one big, huge file, and then you'll see a flag which says, well, that's the end of the bus data. This is the end of the load data. This is the end of the generator data, the branch data, and then the transformer data. And so if I'm somewhat familiar with this, I can see, well, and again, you had to know these fields. We've got here the branch data. This will be the resistance, the reactance, and the charging susceptance. And here we have, here it is, we have the from and the to bus. Those two numbers. That'll be the from bus, the to bus. For the generator data, this is the bus. The generator only connects to one bus, so that's the bus it's connected to. That's the bus. This is the generator here. These are the loads here. So again, this is very cryptic, and it's okay for engineers to use, but it's not something that an operator could ever hope to update in real time as they're running the system. Now, during the probably the 90s, we started to have nice graphical displays as well as plotters, and so we started to see the output of planning programs be shown as you see here. And again, this is not real time. It's not being updated as events change. It's really the snapshot of a study, and so we see generators and transformers and buses. But again, to an operator, this is a gross simplification. This is really a much more complicated structure with multiple breakers for each of these connections and isolating switches. So in summary, the buses were very convenient because we didn't have tabular, we only had tabular input, tabular output. It made it feasible for planners to define, view, and discuss the model. We didn't have graphical tools. It's virtually impossible to build a breaker-oriented model without having good graphical tools to both build it and visualize it. We did go through a transition where our customers were forced to build them, but these were very error-prone steps. And so we didn't have database managers. Literally, this was before companies like Oracle had been even founded and invented. We saw relational databases become very popular during the 80s, but we've had planning programs through the 50s, 60s, and 70s. And so the fact that everything could be related to the bus object simplified that. Models could be updated fairly quickly. I mean, you could edit your text files, and you could maintain multiple copies of those files, so you could have different versions. You could have your model for the spring, the summer, the fall, the winter for this year, as well as future years going forward. We'll see that operating models tend to be a lot more cumbersome, so you don't tend to have multiple operating models. You tend to have one that reflects the real conditions. So let's look at the evolution. Like we said, a lot of these programs of power flow and load flow and stability became prominent on mainframe computers. This is an IBM 360, probably around about $1 million computer with much less capacity than you have on your iPhone and much less memory. But basically, the vendors, Westinghouse and General Electric, who sold a lot of equipment, they invested in building their own load flow and stability. And we saw some of the larger utility organizations, Bonneville Power, WSCC, Philadelphia Electric, literally created, they had very talented teams of engineers. They wrote Fortran code to run these simulations. The way you built the model, it was through card decks, and then you fed that in through the card reader, and you got your printout back through the card, the line printer. I have to admit that And normally it would be a half day or day turnaround. You'd hand your box of cards to a computer attendant, and then they would come back hours or the day later. I used to work the night shift. I literally had one of these dedicated to myself, so I would start there at 10 o'clock and work till about 6 in the morning. And I could get much faster turnaround when I was working my thesis. I still remember that I had a set of code that was a box of cards would be about that long, and of course about that wide and that deep. And I used to, I'd broken my leg playing soccer, so I had to hike over on my crutches to the computer center with a deck of cards and a string bag to kind of get my work done. But it was a good time. And it's interesting, a lot of the codes that were built back then have evolved and have not changed a lot. One of the, the pioneer for planning models and the developer of PSSE was Dr. John Undrell. John was also educated at University of Canterbury in Christchurch, and I had the good fortune to spend a couple of years working under his supervision. And he came back to the US after a brief stint in New Zealand and started at a company called Power Technologies in '72. And at that point, 32-bit mini computers, which were a lot less than mainframes. You could get a Prime 750 for about $200,000, and John wrote software, Power Flow Stability Short Circuit, to run on that, and that would be in Fortran. And that changed the whole game. All of a sudden, these programs became, the hardware and the software became affordable for utilities of all sizes. Well, especially anyone from several thousand megawatts up could afford that. Now that software, PTI was bought by Siemens, and so we see Siemens and the PSSE software go together. And the beauty of that is that the formats were openly published, and they encouraged to have groups of utilities all sharing their models. So you will see all of the eastern United States, all of the western United States modeled with PSSE software. John actually left PTI in '86, and I still remember him saying that programming was for young folks and he didn't intend to write software, but lo and behold, he then worked on another program called PSLF, the Power System Load Flow Software, and that company, Electric Power Consultants, was purchased by General Electric in '94, and that has also become a major product in the marketplace, and it is especially favored in WEC and with all the WEC transmission operators. Again, the formats are openly published, not too different from the PSSE, and so it's been favored in the WEC because the models for dynamics tend to be a lot more complicated. The WEC system is a much more highly coupled system, and John was able to provide both consulting and studies and modeling with that software, and today it's very highly regarded. He's one of the few engineers that can walk into a power plant, observe the plant, take measurements, and go back to the office and program up the models to actually work like the power plant actually works. So that's a very specialized talent. Now, and like I said, in the early days, these programs were tabular, tables in, tables out. Tom Overby, who founded PowerWorld in 1996, had the vision of let's make things graphical. And basically PowerWorld was founded on the vision of having graphical displays to give the users a much better intuitive overview. So here's an example of, here we have a schedule which is, say, 100 megawatts going from Milwaukee to Miami. And so this shows the relative amount of flow that is going on all the different paths from Milwaukee to Miami. And so you can see that based upon the higher, the darker the color, as it goes to red, we're getting, say, maybe 20% of the flow, or 80% of the flow is going on that single path. As we get to the lighter greens, and you've got a smaller and smaller percentage. And so that's a really good example of what we call the parallel path flows. Okay, the power just doesn't go on one route. And we talked about this earlier. You may buy a path from here down through here to send 100 megawatts, but really a whole lot of that megawatts goes on other paths where it spreads out. Here's one with contours. This could be a voltage contour. As it goes blue, the voltage is getting into the lower limits. As it goes red, the voltage is exceeding the high limits. So Tom was a major innovator in graphical displays and has significantly increased their share through that process. And the fact that the models from PSSE, PSLF were openly available without proprietary formats meant that he could go to a customer and say, give me your model and let me run these studies. And that has not been the case in operations, okay? And we'll get into that. So the market for planning has been more open as a result of those de facto standard formats. So the models, the interconnections has grown in size. The scope of the studies has grown. People have gotten to the point where they really need to model the entire interconnection. So today we're seeing models in the 50 to 100,000 bus range. Like I said, planning models can be easily edited. Programs can handle multiple models. It's really just another text file that you're saving. So there's really no limit to the number of different versions of your system that you can save over time. Like I said, they're typically single user, and they run when the user makes a change and makes a request, and they're not connected to the real-time system and not updated with real-time data, and they're not event-driven. The line diagrams are simplified. You can automatically generate the diagrams. It's actually tough to automatically generate a detailed diagram of, say, a breaker and a half or a main and transfer bus. The operator expects those bays to come out in the exact same order that they are in real life. And so that's been a challenge to build those diagrams automatically with computers. Whereas with planning programs, the operators, the engineers are not so fussy about having the exact physical layout of those diagrams to run studies. So let's now turn and look at some of the different types of equipment models that are needed for planning. The PSSE raw file actually goes through a sequence. It starts out with the case identifier, and then it goes through the bus, the load, the generator, the branch data. These are lines, transformers, areas, DC lines, voltage sources, your shunt data. There's some transformer impedance correction tables. The impedance may vary with loading. That's an optional refinement. You can have multiple terminal DC lines with more than two. You can group lines into sections. You have zones, transfers between areas, the owner, and the fax devices, which are flexible AC transmission system devices. So it's a very logical sequence, and basically there's a block of text for each one of those. So we won't go through them all, but I'll go through some of the major objects. So we have the bus data. Every bus in the system has to be uniquely numbered. It is done by area. In each interconnection, a certain range of bus numbers is assigned for each area. So you have to stay within those ranges. Otherwise, you have no guarantee that they will be unique. Giving it a name is optional, but highly recommended, all right, to actually give it the name of a station and then say the voltage level at that station. There's a code. Basically, if it's a load bus with a real and reactive load, you give it a 1. If it is a generator bus where a generator is actually regulating the voltage, you give it a 2. And then we talked about the whole idea of a slack bus. In any interconnected island, we need to have a slack bus which basically takes up the megawatts for the rest of the system. And then you can have one of those for an island. If you don't specify that slack bus, your model will blow up. The actual solution will be ill-conditioned, all right? So you've really got to understand ahead of time how many islands do you have, and then specify one slack bus for each island. And then, of course, our buses can belong to an area, a zone, and an owner. And really, by specifying the bus to be within a certain area, all the equipment that is attached to that bus belongs to that same area, all right? Except for a line will go between two buses. So a line can actually belong to one owner at one end and then one other owner at the other end. And then what's nice is that you can actually specify the voltage and the angle to start the solution. By default, the voltage is 1 per unit, the angle is 0. But if one company has already solved that case, it's really good for them to give the initial voltage and angle to the other neighbors so that they can then use that same case and verify the model. There's actually a technique where you can calculate the mismatches with the existing voltage and angle. And if you take those voltages and angles and you don't get a zero mismatch at every bus, you know something has gone wrong in the way you've interpreted that data or in the transition of that data. So that solved case solution is a very good debugging tool. Sometimes you have to play some tricks. You may have a bus tiebreaker. Remember I said you may have a bus here, and a tiebreaker between them. You may actually represent that breaker as an artificial line with a very low impedance. And you model splitting the bus by actually taking the line out of service. So these sorts of tricks, again, are needed because of this simplification of the buses. Let's look at the line data. Basically, a transmission line is very simple. We have a resistance and a reactance in the series part, and we have a line charging, half of it at each end. So it's called the pi model. So we can give the line a name. We have a from bus and a to bus. We can have a circuit ID. Primarily, if we've got parallel circuits, we'll give, they both will have the same from and to bus, but we have to give it a 1 or 2 or a 3 to represent, to make sure that it's there's no confusion between the parallel lines. We have a resistance, a reactance, a total charging, whether it's in service or out of service, and then we can have 3 ratings based upon the normal, the long-term emergency, and the short-term emergency rating. And basically what we're doing is we're modeling the actual 3-phase transmission line as shown here with the towers. Generated data is a simplification for load flow. Basically, we have the bus it's connected to, the machine ID, is it in or out of service, and we specify a certain generation and a certain reactive, and a voltage set point. And of course, we need to say what bus is it regulating. The generator may not always regulate the bus right at its terminal. The generator may regulate the high side bus, and it's important to make that distinction. Which bus is it actually holding? We have a maximum megavar out and a minimum megavar of what it can absorb. Now remember back from the voltage class, we talked about a generator really has a capability curve. It's like a D shape representing the different thermal ratings of the different field, the stator, and in windings. But for planning, they don't represent that entire curve. They literally is just a single max and a single minimum value. So again, that is a gross simplification. As we get into things like restoration studies, we really need to represent that entire capability curve. We have the status, is the machine on or off? And then we can have a percentage regulation. Maybe we've got 2 generators or 3 generators all regulating the same high side bus. So we can't just let them fight against each other. We actually have to say, well, if there's 4 generators, they're each going to have a 25% contribution to regulating that bus. And that's what this value is. We have a minimum and a maximum, megawatt limit. And then we can have some ownership where that generator may have multiple owners. So really, we look at this, and for planning load flows, we have a very simple model for a generator. Basically, it's either a real and reactive output or a real output and a voltage schedule. We don't represent the dynamics of the excitation system. We don't represent the dynamics of the prime mover. That's because we're basically doing a steady state load flow snapshot. Transformers, let's look at those. For transformers, basically they have a series resistance and reactance, and they have what's called a shunt susceptance That's because when that transformer is at no load, it is literally an inductor, and it is drawing a certain amount of megavars from the system. So that's what this value here, B, is doing. It again it's a two-terminal device, has a from and a to bus. It has an identifier and a name, a flag to show is it in or out of service, resistance, reactance, the charging, the magnetizing, and then a fraction for its ownership. It also has data associated with the winding. It can have a tap. The tap ratio is, we went through the whole process of transformers in the voltage class, remember? That tap can raise or lower the voltage by varying from a nominal value. And it can have a phase shift, and that's what the angle is. Again, remember we talked about phase shifters, and we talked about star to delta transformations, so that's what those values can be used for. It has a nominal voltage, it can have an angle. One of the most common types of angle shifts is a 30-degree shift when we go from the delta winding to the star winding. And I won't get into the details here, but you can go back and look at the voltage control class. You remember that we actually get a phase shift, that if this is the voltage on phase A on the delta side, then the voltage for phase A on the star side actually has the shift. And that's because in this case phase A is along this winding here, and in this case phase A is literally this vector coming from the midpoint to phase A. So that can be modeled. We can have three types of rating representing the normal, the short-term emergency, the long-term emergency rating, and then we can have different control modes. We've got our tap, a minimum and maximum tap. The tap can only go within a certain range. And we've got our minimum and maximum control values. And basically what this is that if that transformer is regulating a certain voltage, there's a deadband that says, well, if the voltage is within that band, I don't want you to be changing the tap. But if the voltage goes above that, then I'd like you to change the tap. And remember, we went through that whole process, is that to raise the high side voltage, you normally raise the high side tap. To raise the low side voltage, you normally raise the low side tap. That's the conventional approach of doing it. So again, these numbers are there to specify the regulating band. We can have a number of tap positions. We can have a step size. Now, in planning, they actually they don't deal with discrete taps. They actually let the engineer will specify an actual continuous value of 1.05, 1.25. And again, that is a simplification of the real world. In the real world, you can only have discrete taps. We talked about taps that went from -16 to 0 to +16. You remember they're actually discretely moving up and down the windings. We went through the whole process of how you change a tap position on a transformer without it causing arcing and flashover. But again, to simplify it, they neglect discrete taps and they just let you specify an actual range. Whereas in the real world, you actually have to round things off to a discrete value. Okay, so that covers specifying taps for the windings. And there's one other thing you'll often run into, is that if we have a 3-winding transformer, then the way they specify the impedances is, imagine that you're doing an open circuit test and you're looking at the we've got basically what we have here is our primary, our secondary, and our tertiary connections. And what you can do is you can connect across you can leave the primary open, leave the tertiary open, and you can connect to the primary, and you can measure the impedance between the primary and the secondary. And that's the value we call Z12. And of course you can do it for the other pairs of windings. Now most planning programs do not inherently model 3-winding transformers. They can model 2-winding transformers. And so as an engineer you actually have to go through a conversion process. You take these values, which are taken from field measurements, and you have to come up with the hypothetical values that you use for this hypothetical transformer. And again, this can get a little confusing for operators because that node doesn't exist in the real world, right? This is what we call an equivalent circuit. This circuit will behave like this circuit as far as what's happening from the different terminals. But inside of it, it doesn't represent the real world, right? So there's a process you have to go through here where we can say that the impedance across this terminal 1 and 2, it has to be the same as this impedance plus this impedance, doesn't it? This one is open. So basically, if we impose a voltage source across here, the amount of current is going to be determined by Z1 plus Z2. And that's the same definition over here. This is how much, what's the impedance? In other words, the voltage divided by the current flow if you have a connection across the primary and the secondary winding. So there's a little manipulation you go through that this matrix here is the inverse of this matrix. So it's just a little step you have to go through to calculate these impedances if you're doing this modeling. All right, so that's a fairly high level but view of transformers. Let's look at loads right now. What's happening, we're seeing that loads have to be modeled in a lot more detail to get the true dynamic effect. And the WEC Load Modeling Committee has said, look, we really need to model different types of induction motors of different sizes, all the way from a small refrigerator to an air conditioner to a big drive in a factory. And then we have to model the actual feeder and then the step-down transformer. But historically, we have a much simpler approach for loads. We say it's basically a megawatt and a megawatt extraction from the system. And the load can be 3 types. It can be a megawatt, megavar value that is constant no matter what happens to the voltage. It can be a value which varies with the, which is a constant current. Well, that means that as the voltage drops, the actual load will drop linearly because the current is constant, power is voltage times current, and so the actual, that gives us a linear dependence. And then we can have a constant impedance, which is basically as the voltage drops, the load is dropping with the square of the voltage. Sometimes we call that the zip. We have Z for constant impedance, I for constant current, and P for constant power. But basically, resistive load, for example, a stove, incandescent lamp, varies as the square of the voltage. Whereas a induction motor, as the voltage drops, that motor keeps drawing the same amount of power. And so an induction motor may be constant power. So depending upon the region, the season, the types of loads, residential, commercial, industrial, you have different load characteristics to reflect the voltage dependence. But again, for power flows, this is a static model. It doesn't represent things like induction motors stalling or starting up or slowing down as frequency changes. But again, the loads, of course, really drive the entire solution, and it's important to get a good estimate of the real and the reactive component. We're getting towards the end, but switch shunts, here's an example of an actual a hose bank, 3 phases, phase A, B, and C, and a whole bunch of capacitors, some of them in series, some of them all in parallel. And to model all of that, basically what we do is we say that there's a bus that it's connected to. It may or may not be controlling. If it is controlling voltage, what are the tolerances for the high and the low that it will allow as a bandwidth? what bus is being, what voltage, yeah, we have to specify the bus where the voltage is being controlled. If we have multiple capacitors on the same bus, then they all pick up a percentage of that. It may start out at an initial value, and it may have a number of steps, and there may be an admittance for each step. But again, you can see with a few attributes, we're modeling a very complex device in the field. And that really is the heart of modeling. You've got this enormously complicated physical device. What are the key things, key attributes, parameters that you have to put in there to model that? So I've gone through with like a flyover of different modeling types, okay? There's a lot of detail. Get a decimal point off by a factor of 10, everything may blow up, right? We had a case in a restoration study. Somehow the line reactance was 1,000 times more than what it should be. And any time the customers would connect any load to that particular line, the whole island would collapse, literally because there was an error there. So it's really important to get the decimal point in exactly the right place. It's important to get the connectivity right. So as you can see, in fact, the more eyes you can have look at these models and validate them, then of course the better off you are. We talked about the importance of modeling entire regions. And one of the other big differences is that for historical reasons, models for operations have pretty much just gone out to the boundaries and a little bit into the neighboring systems. Planning models, there's always been an awareness that you have to model the entire interconnection to get the results correct. And especially when you look at what we call the dynamic stability of the system staying in synchronism. Out west, the historical issue is a lot of power is coming from hydro in British Columbia, and it's been coming through the Bonneville off the Columbia River, and we're shipping that down on the DC line and the AC line to the demand in California and Arizona, especially during the summer. And if you don't study that whole system, you don't get the fact that when there are certain faults on those AC lines, if they're not cleared quickly enough, the whole system goes into loss of synchronism. So it's been inherent, I think, because you can run power flow studies and get away without modeling the full system, but there's no way you can run stability studies and not have the full system modeled. So we have naturally seen engineers get together through those reliability regions and share their models and work as a team to do all of that modeling together. With operating systems, the history has been, well, I collect the data from my system, my substations, my RTUs, and I present it to my operator. Only recently, after, say, the blackout of 2003, was there a need for the wide area situation awareness. And it was only then we started to see, hey, we need to bring in data from the remote regions and create that wide area view. So that tendency towards looking at the wide area view has been a relatively recent thing. And through that, we had the concept of reliability coordinators. That those reliability, for the first time, those reliability coordinators, there's about 14 of them, would have the responsibility for a wide area view. So we've seen the sharing of models for operations come about a lot later in the game. But for planning, basically, we've got these modeling groups. One for the eastern interconnection, including all of Quebec, even though they are actually connected through DC lines and are synchronous. We have this whole group works together. We have WEC, which also has a modeling group, and then we have Texas. And because these are asynchronous interconnections with DC lines, there doesn't have to be a lot of studies that are isolated from each other from a stability point of view. For a DC line, you can pretty much assume that there's a constant amount of power is going to be transferred across that line, and you can run all the studies on this interconnection without worrying about what's happening on the other side of that DC line. So these interconnections, they allocate the bus numbers to all the different areas. They coordinate their winter and summer peak cases. And typically they'll go down to like the 69 kV, but they won't go down to the 34.5 kV level. And what we've seen is that before 9/11, these models could be downloaded. Universities could get them into research. But after 9/11, they are now critical energy infrastructure information. You have to sign non-disclosure agreements with those entities. You have to do background checks on your employees, and you really have to treat that as critical information. On the WEC side, they have a number of modeling task force, the HVDC, the Power Plant Data Task Force, the Load Modeling Task Force, Renewable Energy. And so there are literally dozens of engineers working to both extend the mathematics of those models and then collect the data and share that to get really good, accurate studies. In the East, they have a group called the ERAG, Eastern Interconnection Reliability Assessment Group, and they divide up into some study forums of the Northeast, which is NPCC, Northeast Power Coordinating Council, and part of Reliability First here. The Southeast, which is the eastern part of CERC, and part of Reliability First. And then the Western, which is the Midwest Reliability Organization, and part of Reliability First, and part of CERC, and part of SPP. So they are going through and they're building those cases together, and they are sharing them. So let's look at the pros and cons of planning models. They are available for entire interconnections. They don't require sophisticated data management, largely because of the fact that everything's keyed around that bus and that bus number. It's relatively quick to make model changes, and they have all the parameters to model transient stability studies on that interconnection. Will that interconnection stay in synchronism if you get these types of faults? The vendor formats from PSSE, Siemens, and PSLF, GE are openly available. You can actually download the user guide of not the latest release, but the next to latest release off the website from PSSE and get a description of all those parameters and what the formats are. And they're available to consultants with a non-disclosure and statement of intent with the different regional entities. The disadvantages, the whole concept of the bus numbering and the simplification of this is relatively foreign to system operators. They don't update automatically as the real-time conditions change, as breakers open and breakers close. There has to be a lot of manual effort to do that. They don't consider the actual breaker and switch configurations. There can be certain outages that they ignore. We talked in a previous course about if we have a bus outage, let's say this bus is out for service, and I lose this transmission line here, that line is faulted, those two breakers will open, and therefore that line will also go out of service. A single line contingency will always automatically propagate to a double outage when you have a breaker and a half configuration and one of the buses is out of service. The planning program will totally ignore that. The planning view will be, well, this line popped out of service and there's no ripple effect of the other lines. So you have to be careful. And we talked about as a system operator, you have to understand, if you have an engineer running planning studies to give you limits, you've got to let him know, hey Joe, we have a bus out for maintenance. It's your job. He won't know that. You've got to let him know. We can ignore dependencies when we're doing energization, say in a black start drill. Let's say I'm coming in on this line here, and we energize the other end. This line is hot, and I want to go out and energize, let's see, this line here. The only way I can get to this line is I close this breaker, and look, in that process of closing that breaker, I'm going to energize that line and have a whole bunch of megavars come on in. And then I close this breaker, I heat up the bus, I close this breaker, and now I've come in on this line and I've gone out on that line, which was my objective, But in the process, I had to energize that line and absorb the megavars. You don't see that on the simplified model. The simplified model says, I can energize any one of these, heat up the bus, and then I can go out on any one of these. So again, you don't get that dependency. So really, for restoration studies, you've got to be aware of that. We talked about you don't have the actual generator capability curve. You just got two values. And we don't have the discrete tap configurations. But again, as a system operator, I encourage you to kind of dig in, get or an engineer. We've got to bridge that gap, okay? As a system operator, you've got to understand the results coming from your operations engineer and be able to advise him or her about how there may be a distinction between the real world. A lot of these issues go away when we get true operating models, but I'm just looking about the case where you're using that planning program to help you on the desk be an operator. One thing that did support the widespread adoption of regions is the vendors did openly publish formats, and they would take the approach that if they get one customer in a region using their software, they would work with that customer and say, well, let's get all the neighbors on board and get them to use the same program. When you're selling, say, a $5–10 million energy management system, they make those decisions not based upon what the neighbors have done. In fact, there's almost like a certain pride factor that they really want to customize that system the way they want it. The amount of money at stake is huge, so that there tends to be a lot more factors at stake. Is that vendor giving me all the types of customization and taking care of all my different operating procedures the way I want? So we didn't see that peer pressure for modeling of operating models through energy management systems. But clearly, the utilities working as a group together is a very key part of planning programs, and we see a lot of cooperation across regions. We are starting to see more and more of that right now. We have recently completed the first drills in California, where the Power Simulator product was used for every transmission operator in RTO, and they actually, for the first time, did black start of the whole system, and there was not any of the old type of paper drills. So we are starting to, as we have the need for more regional studies, we're starting to see more sharing of operating models, and we've got a standard called the Common Information Model that I'll cover, which is starting to make that an easier process. And then, of course, they do have the dynamic models for all the different types of devices, so you can model stability. So just to review, we've talked about the applications of planning models, the history, why they evolved, how they evolved, the major vendors that were and people that were involved. We talked about structure. What are the objects? How do they relate? We introduced the idea of the unified modeling language. We talked about all the attributes. We went through all the major components, and we said this is what we're modeling, and these are the types of attributes you have to specify. And then we covered the disadvantages and advantages. So in the next segment, we'll get into operating models, but that's a good place to take a break. Thank you very much.